So I got a couple questions this week about counterexamples, and to kind of answer them all in a single video, I'll just summarize it as what is a counterexample and how can we find one. I think to get a good understanding of this, I'd like to walk it one step back actually to just what is a statement. Now, I'll give a couple examples of this to get started because I think it's a little bit more intuitive that way. But basically, if we just look at a regular English sentence, for example, all math teachers have green eyes, this would be a statement. It can be evaluated for whether it's true or false, right? And you'll be able to determine that pretty quickly, hopefully, if you're watching this video. But we can write this out as a statement. Now, this one is kind of just in plain English, but we can also write more mathematical statements. For instance, I might say the sum of any two even numbers is also even. And this one, again, perhaps feels a little bit more mathematically oriented, but in both cases, these are just statements. Now, to be a little bit more specific, we can actually define a statement as a sentence that is true or false, but not both. And both of these would be examples of that here. All math teachers have green eyes is a statement because it can be evaluated as true or false, but not both. In this case, it would be false. Likewise, the sum of any two even numbers is also even is a statement that can be evaluated as true. Now, demonstrating that that first statement is false was fairly straightforward in our case because we have an example actually of a math teacher who does not have green eyes, right? I specifically have brown eyes, and because this is saying all math teachers have green eyes, well, that obviously can't be true since I'm a math teacher who has brown eyes. For the second statement, to prove something to be true, that gets a little bit trickier. And in fact, we'll save that for a different video. But at least to explore and give you an idea, we can test out some options. For instance, if we looked at 2 plus 2 equals 4. 2 is an even number, 4 is an even number. If we did, say, 4 plus 8, that equals 12. 4 is an even number, 8 is an even number, and its sum, 12, is also an even number. 26 plus 22 is equal to 48. And once again, all three of those are all even numbers. Again, this evidence alone is not enough to prove that this is true in all cases, but just giving a sense of how this might be true. And it turns out that it is. Now, what we can notice here, at least in particular with our first statement, all we needed to demonstrate that it was false was to provide a single piece of evidence to the contrary. We just needed one example of a math teacher who did not have green eyes in order to show that full statement was false. So proving our statement false required a single example to the contrary. And that single example is what we call a counterexample. Or in other words, a counterexample is an example that proves a statement false. And so again, in terms of that first statement, all math teachers have green eyes, I would represent a counterexample to that because I'm a math teacher who has brown eyes, who doesn't have green eyes. And therefore, not all math teachers must have green eyes. The next thing you might be wondering though is how do we find these counterexamples, right? It seems fairly straightforward in the case of the English statement when we can just observe a math professor with brown eyes or black eyes or blue eyes or some other color to prove that one wrong. But how do we do it when it is a more mathematical statement? Well, in some sense, it's going to be very much the same. We just have to observe some instance that serves as a counterexample. But let's look at a couple of examples to see if we can illustrate how we might find those. First, let's find a counterexample to the statement when 1 is divided by a number, the result is smaller. So I'll tell you here in advance that the statement when 1 is divided by a number, the result is smaller, is in fact false. We're just going to see if we can search to find the particular example that demonstrates that, or a particular example that demonstrates that. And the first thing I would encourage you to do here when seeking out a counterexample is to just explore a little bit. Test out some options, experiment with some things, do some trial and error, and see what you can come up with along the way. So for example, we might look at something like, well, what's the result of 1 divided by 3? Well, we know that that is 1/3, and that is smaller than 1, right? So this is smaller than 1. So far our guess of 3 doesn't prove this statement wrong. But we might try a whole handful of other things. And here you can kind of pick any number that you'd like to test it out. Maybe we do 1 divided by 6 and get 1/6 and realize, well, that's also smaller than 1. Maybe we try 1 divided by 10 and get 1/10. Well, 1/10 is also smaller than 1. Maybe we try 1 divided by 100 and get 1/100 and realize, well, okay, that's also smaller than 1. And at this point, you may be starting to see a pattern. It seems like all of the guesses that we're trying aren't actually proving our statement wrong. They seem to fit with what the statement has said. And this is where we can kind of move to our second strategy, which would be to try some different types of options, some different types of numbers, to think outside the box a little bit and see what we might do to try to break this statement, to try to make it false. So I'll say try different types of options. So one thing you may notice about all of the ones that we've tried so far, right, 3, 6, 10, and 100, they're all just positive whole numbers. And so what we might do is say, well, if we've tried all positive whole numbers, well, maybe it would break if there were negative numbers. And so maybe we do 1 divided by -3, and that would be -1/3. Okay, well, that's also smaller than 1. Maybe we try 1 divided by -100, and that gives -1/100. Also smaller than 1. So our first attempt didn't quite work, but that's okay. We can keep experimenting and iterating and trying different options from there as well. So if we've tried positive whole numbers and we've tried negative whole numbers, perhaps we branch out beyond just whole numbers themselves and maybe try something like a fraction. And this is where we could do maybe something like 1 divided by 1/2. And if you recall how we can divide fractions, a division of a fraction is essentially just multiplication by the reciprocal. Or in other words, 1 divided by 1/2 is equal to 1 times 2/1, or 1 times 2, which is just 2. Now this is really helpful for us in this case, right? Because 2 is not smaller than 1, right? 2 is bigger than 1. So what we've found here is an example that proves our statement wrong. Or in other words, a counterexample. Right? Our statement says when 1 is divided by a number, the result is smaller. And what we've shown is, well, actually, when 1 is divided by 1/2, the result is 2, which is actually bigger. So in this case, we have a counterexample, and we have demonstrated that our statement A can't always be true. And so 1/2 is a counterexample. So a little bit of experimentation and trial and error, and a little bit of exploring some different types of options available to us are a couple of strategies that can help us potentially discover a counterexample. Let's do one more to illustrate another common strategy that we can try to help us discover a counterexample. Let's look at the statement, the sum of any pair of 2-digit numbers has only 2 digits. So we're saying if we have any 2-digit number, for example, something like 10, and we add it to another 2-digit number, it must have 2 digits. Now, once again, I'll tell you in advance that this is a false statement, and we're going to be seeking out at least one example to demonstrate that it's false, at least one counterexample. And so just like before, we can try experimenting with some things, right? We might say, for example, well, 22 plus 34 is 56. I'm just pulling these 2-digit numbers off the top of my head. 24 and 34 equals 56. 56 also has 2 digits, so that doesn't quite prove us wrong here. We might look at 41 plus 48, which is equal to 89. Now 89 also has 2 digits, so this doesn't quite get us there either. And now I'm sure if you experiment enough times, eventually you'll get to one. That proves our statement wrong. After all, there's only a finite number of 2-digit numbers, so you will get there eventually. But there is one thing that we can try that will help us get there a little bit quicker. And so for the third strategy that I'll recommend is to try some of the extremes. So to test values at the extremes. This would be like minimum values, perhaps, or maximum values, or other similar extreme values, depending on your particular circumstance. In our particular circumstance, we can look at mins and maxes. The minimum 2-digit number would be 10. So if we added 10 and 10, well, that's just going to be 20. Okay, that doesn't quite get us there when we're working from the minimum option. But what about the maximum option? The largest 2-digit number is going to be 99. So if we added 99 plus 99, well, then what do we get? We get 198. And here we can see we've now crossed that 3-digit threshold, right? Since 198 has 3 digits, this becomes our counterexample. Right, so we know that the sum of any pair of 2-digit numbers does not only have 2 digits, because 99 plus 99 equals 198, which has 3. Thus, 99 and 99 serve as a counterexample. And in particular, searching for that pair by looking at the max value, something on one of the extreme ends, was able to get us there pretty quickly. And so that can potentially be a useful strategy to finding counterexamples as well. To summarize, a statement is a sentence that can be evaluated as true or false, but not both, whether that is an English sentence like all math teachers have green eyes, or a more mathematical sentence like the sum of any 2 even numbers is also even. We can evaluate these one way or the other for their truth or falseness. For statements that are false, oftentimes we can prove them false simply by providing one example to the contrary. We call that example a counterexample. To find a counterexample, a lot of times it just comes down to trial and error and experimentation with some of the different options. You might try different types of options, different types of numbers, whole numbers, fractions, radicals, complex numbers even in some cases depending on your circumstance, or perhaps even other mathematical objects beyond just numbers. The point is that exploring the space and testing and experimenting and working through some trial and error can often help give you some clues that can point you in the direction of a counterexample. And then sometimes, depending on the context as well, looking at values that are on some particular extreme end. Maybe you're looking at the max values and finding the largest ones, and that can sometimes lead to a counterexample. Or maybe you're looking for the smallest values, the minimum values, and sometimes those can lead to a counterexample. Either way, I hope you've found this video helpful and have at least a little clearer sense of what a counterexample is and how you might find one. As you're working through your own statements, if you have any questions about counterexamples or there's anything that I can do to clarify further, please let me know and I'd be happy to help. Otherwise, have a great rest of your day.